Hello to everyone. Thank you for Signe and Ferrari for hosting this workshop and clustering and inviting NEXTCELL. We're happy to be among. Sorry that we couldn't be in person. We would love to, but regarding the schedule, it wasn't be possible. So I will give you a presentation of NEXTCELL in general side, and I will have Yanis, who will help us on the technical side and contribution of FEV France to the project. So me, Zahra Daneshi, as a project manager in the FEV and the project manager of the NEXTCELL. So let's go toward the next generation of high-performance lithium-ion battery cells. In NEXTCELL, we benefit from the close collaboration of STEM partners from academia, industry, and technical consultancies. You can see the familiar logos that we have seen already in different presentations since morning. So in NEXTCELL, the project coordination is with FEV Europe and FEV France, with Thorsten and Serve and me as a project manager. We have SIE as the financial coordination. We have Mariana in the audience also, and we have the AB as the technical coordination of the project. Also some representative from IB in the audience. So the agenda that we are going to talk about is first give an overview about the project consortium, motivation and objectives of the project, then going through a bit more detail about the project structure, and Yanis will help us on the technical contribution of FEV to the project. So as you have already seen the name of partners, we are 17 partners from 8 European countries, 7 member states and Norway. The project is started in January 2023, and so we are in the end of second year. We are waiting to have the good results at the end of the project by December 2026. The budget of the project was about 8 million, so 799, and the financing funding was in the call Horizon Cluster 5. So, as already mentioned in other projects, the challenge of the research and innovation today is lie in the development of advanced material, enabling high power, also high energy and high power densities, thanks to high capacity and high voltage, operating voltage. So the focus here is to adapting the cathode materials, anode materials, and electrolytes and their interplay by considering high nickel NMCs for capacity in cathode sides, also spinel lithium-rich NMC for voltage, and in the anode sides also graphite containing silicon oxide for electrolyte. We are looking for the stabilized formulation. So in NEXTCELL, our goal is to provide a new lithium-ion generation for both high capacity and voltage applications. For that, we are developing and validating the concepts, and also to integrate several innovation and material level for each main components named already. For that, we can say that the goals are to have high energy density, physical and mathematical models, sustainable, cheaper and safer. For high energy density, we say excellent performance in high capacity and high voltage applications. For physical and mathematical models, we say key methodology to optimize and accelerate the research and development process for new technology on the storage technology, actually. And by sustainable, it means optimization of manufacturing process, reducing capital and operating cost of future gigafactories by avoiding the evaporation of solvents and electrolyte filling step. So for cheaper, of course, reduction of around 50% in energy consumption, and by safer, means safe cells, avoiding the presence of low boiling point components in the electrodes and the separator. So the main objectives of the NEXTCELL we can name in 4 acts. The first, of course, is to develop the material requirements for jellified cell concepts. The second is prototyping the concept to TRL6. Of course, the modeling of this jellified concept is the third axis, and evaluation of technical safety and sustainability and cost improvement is the fourth axis of the outcome and the objectives of the NEXTCELL project. So to achieve this, let's go to have some visual presentation of the structure of projects. So in NEXTCELL, the project work plan revolves around 3 main acts. The first, in the main core, you have the prototyping. So for prototyping, we have the requirements specification and requirement specification for these cell concepts and materials. Then we have in the work package 3 the material and development of raw materials and definition of the continuous solventness production of the jellified electrodes and separators. Also, we have the small scale jellified cells, and at the end that we have the larger scale jellified cells for the project. So for these main prototyping sites, we have work package 2 to work package 6 who are involved in the development of, let me go to next slide so you can have the name of partners who are actively working in this axe. So in this part, we have work package 2, which is already done and by the requirements in the first year. And then work package 3, which is in the middle to the end of this development of raw materials, which is one of the main steps of the projects. And we have work package 4, which is responsible for the cell designs and manufacturing at the pouch cell level. And of course, work package 5, which is for electrochemical characterization, thermal aging, and safety tests. Then at the end of these steps, in this axe, we will have the prototyping of large jellified cell. The next axe, as I heard in other projects, they integrated modeling to the other work packages. Here we have separate work package for modeling, which is in continuous cooperation with the other work packages. You can see the lead and main partners on the work package 7. Then we have work package 8, which is the main responsibility on the third axe, which is the technical validation of the cell safety with work package 5, and sustainability, cost and sustainability. yeah, we have work package, work package 1, which is the project management I've presented in the first slide, and work package 9, which is the dissemination and communication that we have, of course, sustainable innovation with the rest of partners, cooperating to the rest of partners. So for the part of the FEV contribution and task in this NEXTCELL, FEV actually has a role in the project management, as you already said, and then we have the contribution to the work package 5 and work package 8 that I give the floors to Yanis, who will present the contribution to the project.
Hi everyone, also from my side. My name is Yanis. I'm a technical specialist here at FEV Europe, which is mostly based in Germany. And I will be talking briefly about what we are contributing in the NEXTCELL project. And as you can see, we have two separate work packages in which we are deeply involved. Number one being the cell testing. Next slide, please. And the cell testing work package deals with the extensive characterization of the prototypes of the jellified cell that will be developed within NEXTCELL, meaning electrically, but also the safety aspects and so on. Next slide, please. And why we are doing this is because FEV has quite extensive testing capabilities, not only for battery cells, but also battery systems all around Europe. And here we can pretty much test anything that needs testing, be it electrical testing inside or outside of the safety window of the battery cell. We can do extensive safety testing. Here, for example, in the middle of the screen, you see our autoclave, which is capable of characterizing cells up to 400 ampere hour capacity in a bunch of different ways. So, for example, arc testing, but here we also have a press. We can do nail penetration testing, overcharge, short circuit, what have you. And in addition to this, we also have a battery cell lab where we are on the one hand capable of opening and tearing down battery cells, which we use for benchmarking purposes. So we at FEV also benchmark entire vehicles and tear them down. And in the battery cell lab, we also have a look at the battery cells as a highly specialized component. Next slide, please. Exactly, and as part of our benchmarking activities, we have had a look at this cell, as you can see right here. It's a rather small pouch cell, 31 ampere hour capacity. And now you would probably ask, okay, what is here the connection to the NEXTCELL project? And within NEXTCELL, of course, we will be testing these prototypes, but these are not yet reality. That said, we are not just waiting for them to come in. We sourced this battery cell specifically because the manufacturer claims that it is a solid state cell. And since I am showing it to you today, you can already reckon what type of technology it is, right? It's a jellified cell. And of course, these are super interesting for us, for our battery system development efforts. So we had a look inside. And today I will show you briefly a few insights on this cell. So next, please. Exactly. When we have a look inside, we typically perform CT scans of battery cells to see how the cell is assembled in its pristine state, whether there are any defects, what is the layer structure, and so on and so forth. And for this cell specifically, we see that there's really nothing out of the ordinary. We have the typical Z layer assembly with the separator and really nothing special. So in the next step, we have to have a look inside. Next slide, please. And what we found is pretty much summarized right here. You know the three components, cathode, separator, and anode. The anode, starting with it, is a typical composition. It's mostly artificial graphite and has roughly 8% of silicon oxide. The separator is quite interesting because it is a PE membrane, as it is pretty much standard in most of the battery cells on the market today. But what makes the separator quite special is that it has an aluminum oxide hydroxide coating on both sides of the membrane, which is, let's say, somewhat special, but not out of the ordinary, I would say. And then lastly, looking at the cathode, here we have a blend of NMC 532 and 811, and exactly. So looking at this, we still don't see much that is particularly special. So for this, we have to have a closer look. And please go to the next slide. Exactly. This is the most interesting part of this cell. Here we are looking at the cross section of the cathode. You see the NMC active material particles and the void volume, which you would expect for a conventional liquid-based cell, has this solid material that is occupying all of the pore, not all, but quite a significant fraction of the pore volume. And exactly this is the jellified component of this cell. And now you would probably ask, what is the benefit? And for this, we have the next slide. Here we have a comparison of, so what we are looking at here is a safety test of a conventional NMC cell, as you would find it in most electric vehicles today on the left-hand side. And on the right-hand side, we have the jellified cell that I have shown you before. And what we're doing here is we are doing a nail penetration test. So we're punching a nail through the battery cell. And so now let's see what happens. Right. For the conventional cell, we see what we would expect. We have flames and an explosion, which cause a huge safety hazard within a battery system of an electric vehicle. And we see the complete opposite for the jellified cell on the right-hand side. In fact, we do not see a thermal reaction, and the maximum temperature that we observe during the nail penetration test is 59 degrees Celsius, which does not pose a risk of a thermal runaway event or thermal propagation. And this, of course, has very big implications for the way we integrate these cells into a battery system. One outlook I would give here is that for this cell, which has an energy density of 270 watt-hours per kilogram, with this safety behavior as we've seen it, we could think about integrating it similarly to an LFP type cell, which would, of course, increase the battery system level energy density substantially. And now would be a question, okay, where is the drawback of this type of design? Because there must be some drawback. And if we have a look at the cycling performance, we actually see that the cell does not perform badly in the cycle life. So while we would expect that maybe a trade-off has to be made between safety and lifetime, this is actually, as we see it, not the case right here. Even at rather fast cycling rates of 1C, 1C, the cell does not suffer too much and can deliver a competitive lifetime. Exactly. Next slide, please. And since this is a super interesting technology that will be coming to the market very soon at a broad scale, would be my impression. We need to know if it can be cost competitive, because this is, of course, a very important aspect. And we at FEV have been modeling battery cells for a long time. And now we are focusing on modeling this type of battery cell within NEXTCELL. And next, please. Exactly. And this is an activity that is part of the work package 8, where we look at the sustainable production and material recovery with our partners. And here, next slide, please. I won't go into all of the details, but how our cost modeling works in principle is that we try to assess all of the cost rates of the materials, of the cell design, and of course, of the production scenario. And we have to first up modify our conventional battery cell model as we would have it for the cells that are on the market today for the new type of battery cell that is developed within NEXTCELL, meaning the new production processes, the new materials, and so on. And these new inputs are then combined within the cost model, and then we, at the end, have a direct comparison of the cost breakdown between a, let's say, standard cell as it is on the market today and the jellified cell that we are developing within NEXTCELL. Exactly. And with this, I think I'm already at the end of giving a short overview of our contributions to NEXTCELL.
Thank you, Yanis, for the presentation.